morning, which is Chris Lovell, learning the relationship between Galaxy Spectra and their star formation histories.
Okay, so I'm going to present a project I've been working on mostly with Viviana Acquaviva here at City University of New York. Slightly different approach to some of the talks you've heard today. It's actually a regression problem. But essentially what we're trying to do is learn this relationship between the spectra of galaxies and their star formation histories, which is essentially when the stars in that galaxy were formed. So in traditional SED fitting approaches, you use an SPS model, a stellar population synthesis model, which models the emission from stars as a function of age and metallicity. You combine this with some SED fitting code, typically using MCMC approaches, to then maximize the resemblance between your models and your spectra that you want to infer the star formation history from. And this has been very powerful, there's been a lot of great achievements in this kind of approach, but one of the big limitations to this approach is that you don't have very good priors on what the star formation history should look like. There's a lot of degeneracies in the spectra that can mask this, the presence of or the inference of the star formation history, such as outshining by young stars, the age metallicity degeneracy between stellar populations. So we've decided to choose a new approach that uses, funnily enough, machine learning to combine these SPS models with cosmological simulations where we know the true star formation history, and then train a convolutional neural network to learn that relationship between the modeled spectra and the star formation history, and then apply that to observations. So this is a different approach. It has perhaps slightly different biases to traditional SED fitting. So we do this, I'm just going to go through like the general setup of the model. So we use two cosmological simulations, Eagle and Illustris. So these are reasonably state-of-the-art simulations, 100 megaparsecs on the side, to have quite well-sampled galaxy populations. We select all galaxies above 10 to the 10 solar masses, and then generate spectra for those. So this is the star-forming sequence in those two simulations, and you can see that they, despite being kind of state-of-the-art, show quite different behavior on this map, which will become important later. So we've heard an awful lot about CNNs today. So we use a CNN architecture, but applied to just these 1D spectra rather than 2D images. If you're interested in that, come speak to me afterwards. So our features are the galaxy spectra, and then our predictors, we logarithmically bin the star formation history back in time, so that we sample more recent star formation finer than older stellar populations. So to generate the spectra, we use a quite simple model. We use Python FSPS, which is a SPS model that also includes nebula emission from Nell Byler's recent edition. So this is an example spectrum from our model. The green here is the intrinsic emission directly from FSPS. And then we use a simple prescription for dust that links the attenuation to the mass and metallicity of star-forming gas, and that attenuation spectrum. And we get reasonably good color distributions. These are for Eagle and Illustris using this model. So to try and, just to give you an idea of what we're actually doing here, here's some example star formation histories and our predictions for them. So each of these plots shows log look-back time along the x-axis, the star formation rate as a function of that look-back time. The blue here is the true star formation history. This is using the Illustris simulation. And the red is our prediction. And these go from our best prediction over here to some of the worst predictions in our model. So you can see that we successfully pick up episodes like galaxies such as this that have very old stellar populations but very little activity recently. We also pick up more subtle changes in the star formation history, rises and falls. However, more sudden changes at kind of intermediate ages kind of get missed out. We predict slightly smoother histories. So when I said that we went from good fit to bad fit, our loss function that we use here is a thing called symmetric mean absolute percentage error. So this gives, it acts basically as a percentage error in the kind of low error regime, but allows you to give a fair evaluation. It's not biased by the stellar mass. We have quite a large dynamic range in stellar mass, and also allows you to predict for zero value bins. So this is essentially showing that symmetric mean absolute percentage error, the SMAPE, along the distribution of that for different models. And in the top here, we show the comparison of our CNN architecture to a tree-based method, extremely randomized trees. The CNN seems to outperform it much better, even with quite considerable hyperparameter optimization. So we get percentage errors, average percentage errors across the whole history of around 12 to 13%. We also add experimental noise to our spectra. So true, every observation of the galaxy has some experimental noise. We use a signal to noise of about 50. And we found that obviously when you do this, you increase your SMAPE error by about 1 to 2%. So not a huge increase, but it does somewhat obscure the underlying relationship. But one of the powerful things of doing this is that we can actually resample the noise multiple times. And this is analogous to observing the same galaxy multiple times. So we're not increasing our training set of star formation histories, but we do give the machine more information on the relationship between spectra and star formation history, and it's able to learn and generalize better. So when we do this 4 times, so we resample the noise 4 times for each spectrum, we actually get better results than the no noise case. So we've also looked at just increasing the noise as well. So when you go up to a signal to noise of 20, this leads to quite a considerable increase in your percentage error, but resampling that again reduces that considerably to below 15%. So as I mentioned, in traditional STD fitting, you see a lot of these degeneracies and effects that can obscure your relationship. We wanted to test that we weren't also seeing some biases in our predictions. So because we just select galaxies above 10 to the 10 solar masses, the galaxy stellar mass function is very steep. So the numbers of massive galaxies are much lower than the numbers of very low mass galaxies. So we might expect to overfit to low mass galaxies. But we don't see this when we plot the correlation coefficient of the SMAPE with stellar mass. We also don't see any correlation with star formation rate with the percentage error, which you might see if there was outshining effects. And similarly with metallicity, we see very little impact there, which we think may be due to the quite coarse sampling or binning, of our star formation history. So we also wanted to try and estimate kind of the errors on our estimates. So we haven't heard that much about that today, I guess because we haven't heard much about regression problems, but we wanted to give some estimate of what that error would be. So we produce an error that's a combination of what we call experimental errors, so from the noise in the spectra, and the modeling error, so the residual in the test set. So to estimate the spectral errors, we simply sample the noise multiple times, feed this through our model, and then look at the distribution of predicted histories. And we find that this is kind of quantitatively dependent on the star formation rate. Is larger for the dust attenuated spectra for young populations, but is much subdominant to the modeling error. So the modeling error is simply estimated from the residuals on the test set, and this kind of dominates, at least for our fiducial signal to noise of 50. But when we do that, that's what these error bars here are on our predictions. So we have some estimate of the uncertainty from the model and the experimental errors. The experimental and modeling are added in quadrature. So the reason we use eagle and illustrious together is to try and get an idea of how well the model is learning a general relationship between spectrum and star formation history and not overfitting to a particular simulation. So the danger of using simulations, which we've heard a lot about today as well, is that you learn or overfit to this particular simulation, and then when you apply it to real data, your predictions are going to be wrong. So to kind of test this, we used eagle and illustrious, and then we used the eagle model and applied it to illustrious data, and vice versa. And what we found is you do see an increase in the percentage error, as kind of expected, but it's not terrible. So we see an increase of about 3 or 4% between changing the data set. We also looked at how well we recover the star forming sequence, so the stellar mass star formation rate relation. So if we were overfitting to a particular simulation, we might expect to just reproduce the star forming sequence of the data the model was trained on. But we don't see that, so we actually recover the star forming sequence of the data that we test on. So we recover for an eagle model given illustrious data, we get the illustrious star forming sequence. So finally, we then applied this to real observations, so SDSS data. We chose the DR7 catalog because this has been used with VESPA, which is another star formation history, or bin star formation history estimator. So we wanted to do this comparison just to kind of see how they compare. We're not saying that one model is better than the other. They use very different approaches. But it gives us an idea of just kind of the differences between the two approaches. We selected SDSS galaxies by their GNR magnitudes in sample. So as you're probably all very aware, the machine learning approaches don't work very well on out-of-sample data. So we've used this quite constrained cut, at least for this part of the project. We're looking at extending this, and we're kind of limited, I guess, by the spectral modeling of the simulations. So this is what we get. So this is the median star formation history on this side, and here are some examples with similar stellar mass estimates. So the green here is Vespa, which you can see is quite noisy, has big jumps, and also like quiescent areas here. Excuse me. And the orange and blue are Illustrious and Eagle, respectively. So we predict much smoother histories that are more consistent with cosmic star formation rate density estimates. And we don't see these kind of peaks that you see in Vespa. So this shows the kind of influence of our training data, our training prior. And to kind of emphasize that, the dotted line here shows the input training star formation history. So whilst they're not identical, we're not just predicting our input training data, but the prior from the simulation is very powerful and very informative. So we also, given the very different shape of the median star formation history, we actually still recover stellar masses very similar to Vespa. So this is our is that the estimate? Yes, estimated masses here and the Vespa masses. And the scatter's kind of within 0.2 dex. And now that we've kind of got these star formation histories from our simulations, we can actually start doing a bit of science with them. So this is a split of the median star formation history with predicted stellar mass from lower mass objects to higher mass objects. The orange here is Illustrious, the blue is Eagle. And one of the interesting things we see here is the impact of the training simulation. So Illustrious galaxies at low mass, the model trained on the Illustrious galaxies tends to predict younger median ages for those objects, whereas the Eagle galaxies have much earlier peak star formation histories across the stellar mass range. So we've heard a little bit about self-organized maps from James Geach, which is another way of looking at kind of the spectral similarity. One of the big limitations of this approach is if your spectra from your simulation are not representative of the true universe, then you put garbage in, you get garbage out. So in order to try and assess this spectral similarity, or whether there's any synthetic gap, so a gap between our simulations and the true observations, we use a technique called T-distributed stochastic neighbor embedding. So this is kind of similar to self-organized maps in that you take a very large multi-dimensional parameter space and then collapse that down to 2 or 3 dimensions. And it's mostly used in the machine learning community for visualization purposes. So these axes don't represent anything physical or meaningful, but each one of these points is a galaxy. And this is the distribution of the SDSS galaxies that we selected, colored by their GR color. And then the plots here on the left, the middle and the right plot, the dark gray in the background is the SDSS distribution kind of in the background there, and then the Illustrious and Eagle galaxies are overlaid. So this approach is kind of slightly sensitive to the hyperparameters you use, but we do see, at least for this realization, the very good spectral similarity between the Eagle and Illustrious galaxies. They kind of cover a very similar space. You don't see many large outliers. However, there are areas at the edges of the distribution where you see SDSS galaxies and no simulated galaxies. So this suggests that we don't either, our synthetic or our spectrum modeling is not sophisticated enough. We use quite a simple dust model and a simple prescription for dust using radiative transfer techniques or more advanced spectral modeling techniques. Might be able to improve that. But we also have quite small boxes from Eagle and Illustrious. We don't sample many extreme environments, such as massive clusters, which you may see more of these very, very red or very, very blue star-forming objects in. So using larger, better simulations, you'll get a more representative training set. So I'll just leave my conclusions up, but thank you very much.
Chris, have you time for questions?
So I was wondering, how did you actually assess that the model trained on one simulation is not just overfitting? Because the 2 histograms to me looked pretty different.
You mean on the SDSS data?
I thought you trained on one and tested on the other simulations. Like, yeah, that one. I mean, when you were comparing your noise and no noise, the difference in those histograms was much smaller, right?
Yeah. So we do see an increase of about 4%. So the SMAPE gives you a percentage error across all bins. So you can think of if you were to predict a flat star formation history of, say, 10 solar masses per year across all of those bins. So 10% plus or minus 1 around that. So we're not actually, compared to some other SED fitting techniques where you see dramatic failures for intermediate age stars or dramatic misestimates of the total mass, 16% is actually still pretty good. I can't give you, so I haven't done an assessment of some other SED fitting star formation history technique that uses the same bins. So obviously this is very sensitive to the bin number, et cetera, et cetera. So I can't give you a fair comparison with another one. But yeah.
It's just a comment. I just want to say I really appreciate the attention you paid in your talk to validation and generalization, which hasn't come up so far.
Thank you.
Any more? So can I be cheeky as a chair and ask a question? So I really like the test, the intersim test you've done here. I wonder how much that's just telling us that there's a convergence in stellar synthesis models, and that those that those two simulators are using the same kind of stellar synthesis models. And I think perhaps the answer is in your last work where you were looking at the comparison with the Sloan and looking at that. But what are your thoughts on that?
Yeah, so we did test other SPS models. So we used the Bruzois and Charlot 2003 models as well. In terms of the intersim tests and everything, it all worked very, very similarly to FSPS. So the CNN, it still learns that mapping, which is a reasonably simple mapping between the simulation. Each star particle basically has an age and metallicity, and you map that using FSPS. And it was able to learn that no matter what the SPS model was. Adding in nebula emission did help, so it seems like those nebula emission lines and absorption does actually give more features for it to learn, as particularly young stellar populations, obviously. But the issue with BCO3 was when we went to the observations. So those are quite old models now, and the field's moved on quite a lot. And we found that we were getting very biased stellar mass estimates compared to the observations. So those using the more updated SPS models seem to give much better results compared to the observations.